Hi everyone, my name is Yitai. I am a second-year PhD student at the University of Maryland. Today I'm going to present VEST, Verified, Secure, High-Performance Parsing and Serialization for Rust. This is a joint work with a list of collaborators from the University of Maryland, Carnegie Mellon University, Microsoft Research, and Northeastern University. First of all, why do we care about parsing and serialization? Well, because binary formats are everywhere. It can be your everyday document formats like PDF, zip, or tarball. It can be some executable files like the Linux ELF file format and WebAssembly binary format. Or it might be some security critical formats like some cryptographic handshake format, certificate format, the VPN format, or some transaction formats. Now imagine you are building apps utilizing any of those formats. How are you ever going to interact with other apps? Well, you have parsers and serializers at the boundaries of your app, where the serializer takes some high-level representation of your data and encodes and writes a bunch of zeros and ones to the outside world. The parser, on the other hand, takes some arbitrary byte sequences from the outside world and translate it back to some high-level data structure for programmers to operate further. Unfortunately, secure parsing, or input validation more generally, is extremely hard. In fact, it's ranked among the top 5 most dangerous software errors in the past years. This is primarily due to the conflicting goals that programmers often find hard to balance, namely the performance and security of the parser implementations. Usually, the more optimizations performed, the easier the implementation is deviated from complex format specs, hence more vulnerable to security attacks. Recently, several papers have identified high-profile attacks against binary parsers, especially when the parser and the corresponding serializer are not the inverse of each other. In fact, one of the award-winning papers this year at the USENIX Security is this paper about parser ambiguities. It identifies and exploits a lot of novel attacks based on dubious parser implementations. Our approach to secure parsing is VEST, a verified, secure, performant parser and serializer generator for Rust. VEST provides high-performance implementations for zero-copy parsers and in-place serializers. Each VEST parser and serializer are guaranteed to satisfy a list of properties, from memory safety all the way to soundness and completeness of our implementations, as well as the advanced security properties like non-malleability and non-ambiguity. All of these properties are crucial in preventing various kinds of parsing attacks. Now we only use Safe Rust, so the Rust compiler provides us high assurance for memory safety, more or less for free. We also use Verus, a state-of-the-art Rust verifier, to formally prove the rest of the security properties. Importantly, even regular programmers who don't know about formal methods can still use VEST, as VEST is able to generate verified parser and serializers from a high-level format description language. Now let's take a look at how regular programmers would interact with VEST. Programmers start by looking at external format specifications and translate them into a VEST file. This file basically defines all the structures, constraints, and dependencies present in the format. Then they can invoke the VEST DSL compiler to generate a Rust module, which contains the corresponding Rust data types for the format defined in the VEST file, the parser and serializer input specifications, as well as their security proofs, and the performant implementations. This process heavily relies on VEST-lib, a formally verified Rust library that we have developed, and enables high proof automation, fast verification, and performant implementation. Once the generated module is mechanically verified by VERS, programmers can confidently integrate VEST and the generated module with larger verified or unverified Rust projects. Indeed, VEST has already been used by several projects. The OWL compiler, for example, used VEST to generate constant-time parser for cryptographic protocols. The Verdict project used VEST to build formally verified X509 certificate parsers. Both work appear this year at USENIX Security. As I mentioned, the key to VEST is its combinator library called VESTlib. In total, VESTlib has 10 primitive combinators and 9 higher-order combinators. The primitive ones include those for various kinds of integers and byte arrays. The higher-order ones include those for sequential composition, choices, repetition, and more. Each of those combinators are proved for non-malleability and non-ambiguity, and they are carefully built to avoid unnecessary copy or allocation. I'll talk about in just a bit how we leverage Rust trace system to achieve full compositionality, but let's first take a look at some example formats that can be expressed in VEST. Here, message is a classical binary format. It uses the TLV scheme, which is a struct with 3 fields: the tag, the length, and the value. Notably, the content of the value depends both on the length and the tag. To specify this format in a compositional way, we can leverage combinators in VEST. Here, I'm composing a nested pair of integers, and based on the value of the tag and the length, I interpret the rest of the format as a message 1 or message 2, each of which consumes exactly len number of bytes. Now, if you have an object like this in Rust, VEST actually allows you to call the spec parse and spec serialize methods, which automatically gives you a formal mathematical model of the parser and serializer for this format. Now, with the same VEST combinator specification, you can also automatically derive the formal proofs of security and correctness for this specific format. More importantly, again, using the same VEST combinator representation, you get the verified performant parser and serializer implementation against the format spec. Now, let's step back and take a look at how VESTlib use Rust traits to make all this possible. At a high level, we have a spec combinator trait consisting of the mathematical structured format, as well as is straightforward functional parser and serializer specifications. At a low level, we have the combinator trait, which defines the efficient data type with format, as well as the zero-copy parser and in-place serializer implementations. We use VERS to verify that the performant implementation obeys the mathematical spec. Additionally, we leverage Rust trait bounds to enforce that every combinator has a view of this secure combinator trait, which in turn proves the advanced security properties of the specification combinators. Now, the end result is that we can build a single combinator definition using VEST-provided combinator primitives to represent the format. To represent the format's mathematical structure, its parser and serializer behavior, the correctness and security of proofs, and the performant implementations. Also, by eschewing higher-order functions in most places, we avoid using quantifiers and make verification very fast. As for the case studies, we use VEST to automatically generate the parser and serializer for Bitcoin block format, the TLS 1.3 handshake format, and the WebAssembly binary format. We compare the execution time of VEST generated code with unverified industrial baselines. including Rust Bitcoin, Rust TLS, and the current lift wasm parser. Now, best execution performance is on par or better than the unverified hand-optimized parser and serializer implementations. We also compare the time of verifying vest generate code with AirParse, another automated parsing and serialization tool verified in F-star. As you can see, in this log scale chart, vest is orders of magnitude faster than AirParse. This is in part thanks to Varus, which was built with verification performance in mind, but a lot of the vest trait-based design also helps greatly in terms of verification time. Vest is still under active development. We're currently looking at extending Vest to support recursive formats, to have bit preciseness, to support pointer-rich hierarchical formats. And towards those goals, we would add features to our parsers like parsing actions, error recovery, and nonlinearity during parsing. To conclude, I've presented Vest, a verified, secure, performant parser and serializer generator for Rust. Vest provides zero-copy parsers and in-place serializers that maximize performance, but at the same time is proved sound and complete with respect to its spec, and also some advanced security properties like non-malleability and non-ambiguity. Importantly, Vest provides a generator that can translate high-level format specifications to this low-level implementation that enjoys all the properties that Vest guarantees. Vest is open sourced. You can scan this QR code to check out our GitHub repo. My email address is also attached here in case you have any questions, comments, or want to try out and play with Vest. Thank you so much.